All right. Thank you so much for the award. I'm really honored and humbled by the award to be here with you today and to have the opportunity to tell you about my research after this amazing lineup of speakers. So let's jump right in. In the last few years, there's been a really spectacular progress in many subfields of AI. In computer vision, we've seen some pretty massive performance improvements on a range of key tasks like image recognition. We now have models that perform comparably to humans on pretty extensive and challenging benchmarks like ImageNet. And we've heard about these kind of advances in Jitendra's talk too. Similarly, in speech recognition, we have models based on deep neural networks that achieve performances comparable to that of humans. And they're good enough that they're being deployed on hundreds of millions of devices all over the world. As another example, advances in reinforcement learning have enabled computer agents that can beat the very best human players on a range of games, including the highly strategic, very complex game of Go. But it's really the entire field of AI that is booming based on what I've seen in the last few days at the ICML and IJCAI. There is just so much excitement, so much progress in pretty much every subfield, from theorem proving, SAT solving, knowledge representation, multi-agent system, robotics, natural language processing, and so forth. So it's pretty clear that all these technologies are going to have a pretty major impact on society and on essentially every sector of the economy. It's hard to predict exactly what these changes will be, when they will come, but I think we can get a glimpse of what's going to happen. For example, if we think about how existing technologies from computer vision, robotics, planning are being used in autonomous vehicles, how that is going to revolutionize transportation, or how advances in robotics and automation are already disrupting logistics and retail, and how that could have a major impact also on our home environments. So it seems like even if we just think about existing technologies without even trying to consider the ones that we are developing, these technologies really could have a profound impact on the economy inside pretty much every workplace. And so it might really be the case that we are on the verge of a new industrial revolution, as some scholars are claiming. Now, given this massive transformative potential, to me, the key question to ask is, how do we make sure that these technologies are used to promote the well-being of humanity throughout the world? How do we make sure that they don't become like not just used by a restricted number of technology companies, or they don't become a catalyst that further increases inequality, but they really benefit society at large? So I think the challenge that we have right now, and it's the one that I want to put forward in this Computers and Thought Award, is how do we design interactions between computers and humans to actually solve our society's most pressing problems? Because our society is facing some pretty formidable challenges. There is close to 1 billion people around the world living in extreme poverty, hundreds of millions of people that don't have enough to eat. What you see here are the 17 Sustainable Development Goals. They were identified by the United Nations a few years ago as being essentially the key priorities that the international community should be focusing on. And you see things like ending extreme poverty, fighting hunger, finding new sources of affordable and clean energy, taking action against climate change, reducing inequalities, and so forth. So clearly, these are very important problems. They're also challenging. And what I will try to argue in this talk, drawing examples from my research, is that AI can and should play a role in addressing these problems. So one of the challenges, one of the reasons this problem is so hard, is that these goals that we're setting, they are very, very hard to measure. It turns out that we know very little about what's going on, especially in the poorest part of the world, and there is this big and growing data divide between developed countries, where we're flooded with data, and developing countries where there is literally a data drought. And for example, if we think about poverty, that's ending extreme poverty is the goal number 1 on that list. The way we typically get our data is through nationally representative surveys. So surveys are expensive. You actually have to send people on the ground to collect data. And as a result, they are done very infrequently. So here I'm showing a map of the African continent. For every country, I'm showing the availability, the number, basically, of nationally representative surveys that were done in the decade from 2000 to 2010. And as you can see, many of the countries are white or close to white. And what that means is that there is no data for that country for that entire decade. So as you can imagine, with this kind of data, it's very, very hard to track whether we're making progress toward this goal of ending extreme poverty, very hard to figure out if policies are working or not, very hard also to do social science research if you want to try to understand what are the environmental or political or social kind of like drivers of the variation that we know exist on the ground. You just don't have the data to do this kind of research. Now, on the positive side, we're getting access to high-resolution satellite images for pretty much every corner of the world. And these images, they contain a lot of information about these kind of socioeconomic indicators that we would like to measure and track over time. So you see here some examples. On the left, there is a busy shipping yard. In the image, you can almost count the containers. You can see the ships. You can see information about the kind of infrastructure that is available, roads, buildings, houses. You see information about economic activities like the mine on the right, or fields, or crops. You can even see how the landscape is changing over time. Now, the challenge is, of course, how do we make these inferences automatically so that we can apply these ideas, we can make these inferences on hundreds of millions of images, and we can cover large geographic areas so that we can also sort of like keep this information up to date as the situation changes on the ground. So this seems like a perfect application of all these recent advances in computer vision, machine learning, artificial intelligence broadly. We would like to build a system that takes as input high-resolution satellite images. It identifies all kinds of visual features that are relevant for essentially economic development, and then uses them to predict various indicators that are relevant for the Sustainable Development Goals, for example, various kinds of poverty measures. It turns out that the challenge is that although we have essentially an infinite amount of images, we have very few labels. For very few of them, we know what's going on the ground. The reason is that we have very few surveys. That's precisely why we would like to build such a model, because we don't really know what's going on the ground in these kind of countries. So what this means is that you cannot just take your favorite deep neural network and just train it end-to-end on a lot of labels. We just don't have enough data to get good performance if you try to do it that way. So what we had to do in this science paper was to show that we had to come up with some new techniques to basically try to get high accuracy using try to get around this kind of labeled data scarcity. So the first thing we looked into is transfer learning. It turns out that we have satellites that take images over the Earth, not only during day, but also during night. And the amount of nighttime light that you see for a particular location is actually heavily correlated with the level of economic development. So here you see an image taken from space during night of East Asia. If you can't recognize it, that's South Korea, that's China, and in between, you have North Korea. So it's essentially completely dark at night to the extent that South Korea almost looks like an island, right? So clearly, there is a strong correlation between how bright an area is during night and how economic developed that area is. So what we can do is we can exploit this signal as a form of weak supervision. We can train a large neural network to predict for any location how bright or dark that location is going to be at night just by looking at the corresponding daytime image. And in order to do well in this task, the network will have to figure out, for example, that if there is a forest, then that area is probably going to be dark at night, while if there is some kind of fairly developed city, like the one on the right, then that's going to be probably fairly bright, right? And the advantage of this is that we are in the regime where deep learning works very well. We can generate a training data set as large as we want, effectively. And so we can actually train a very complex model and hope to be able to learn to identify the kind of features that we care about, like roads, like houses, things like that. And indeed, the model does. There are some of the filters that the model learns while trying to solve this task. You can see that it learns how to identify roads, waterways, houses, tall buildings. My favorite one is the swimming pool filter. The model figured out that swimming pools are highly correlated with how wealthy an area is, and that's a good feature if you're trying to predict whether that area is going to be dark or bright during night. And what's interesting here is that we never provide any label, okay, this is a road, this is a building, this is a swimming pool. The model came up with these kind of features automatically as being useful for this prediction task. Now, given that we have these features, now we can try to attack the problem of actually predicting poverty, which is the one we wanted to solve. We have a few locations for which we have survey data. What we can do is we can take one location, we can take the corresponding image, we can feed it into this pre-trained model. We get this kind of rich visual features that I showed you before. We can do that for all the locations for which we have survey data. We can also look at the corresponding indicators that are in the survey for these locations, and then we can train a simple, linear regression model effectively to try to predict how rich or poor, or try to predict survey indicators directly from the images. After we've trained the model, what we can do is we can take locations for which we don't know what's going on the ground. We can take the corresponding images, we can feed them into the model, and we can come up with predictions. And we can do that for all the blue dots, for all the locations at which we care about making predictions. Now, this works reasonably well. One limitation is that it's going to make predictions independently at each location. And we know that there is a lot of spatiotemporal structure in the kind of signals that we're trying to predict. Things change slowly over time and also to some extent over space. So to take that into account, we built this model based on Gaussian processes. The idea is that we're going to make prediction not only based on the visual features, but also on the position, latitude and longitude. And then we use this Gaussian process model, which is a model that is often used in geostatistics, also in machine learning, to effectively make the predictions. I'm not going to go into detail on how that works, but you can think of it as a model that enforces spatial correlation. Now, the other advantage of the Gaussian process model is that it allows us to quantify uncertainty. What I mean by this is that if we take a location for which we want to make a prediction, one of these blue points, and we feed it into this model, the Gaussian process will not only make a prediction, which is shown as a solid black line there, but it will also tell us how uncertain the model is about this prediction, which is basically pictorially shown here as the width of that uncertainty envelope. And essentially, the model quantifies uncertainty by checking how similar the blue point is to one of the red points, which are the labeled ones, the ones for which we know what's going on the ground. So the idea is that perhaps we can use this uncertainty quantification to do semi-supervised learning. The idea is that although we have very few labeled examples, we have essentially an infinite amount of unlabeled data. And so perhaps we can exploit all this unlabeled data to get better performance. The way we do it is by trying to do this. We're going to try to change the parameters of our neural network so that not only we can fit the labeled data as well as we can, but we're also minimizing the uncertainty at the unlabeled data points. Basically, what we're trying to do is we're trying to identify features such that the unlabeled data points look more similar to the labeled ones. And that provides a good inductive bias that gives us a significant performance improvement, and it works well on a range of other regression problems. Like if you can look it up in the paper, it works well across a range of benchmark problems, not only in this poverty prediction task. So now that we have trained the model, we can see how well it works in practice. We've applied it to a number of African countries. Here are the results for Uganda. Every dot here corresponds to a location for which we have survey data. This is a cross-validation plot. So what we do is for each location, we pretend we don't know its value. We train a model on everything else. We make a prediction on that point, and then we check how well we do. And on the x-axis, I have the observed value, which is the ground truth, which we know. On the y-axis, I have the prediction that our model makes based on the images. Ideally, you would want to be on the diagonal. That would mean that the predictions are perfect. And you can see the model is not perfect, but it's capturing something like 70% of the variation in the data, which is extremely good. Like when I showed these plots to my collaborators in economics, they couldn't believe that we could get these kind of accuracies because it's so much better than anything that was available before. The nice thing about this model, though it's not perfect, is that it's very scalable, it's very cheap. The only thing that you need are images, which are widely available, they're updated frequently. And so what we can do is we can take any country we care about, let's say Uganda or Tanzania here. We essentially download images that cover the entire country, we feed them into the model, and we can come up with this extremely high resolution, actually unprecedented resolution, poverty maps that we can also keep up to date. As soon as we have new images, we can just feed them in and keep the maps up to date. So we got a lot of attention on this work from the media. Bill Gates was tweeting about this. It was also mentioned in the White House report on the future of AI. It was also very well received by the scientific community. We were actually selected by Scientific American as being one of the 10 world-changing ideas of 2016. organizations from small NGOs, non-government organizations, to larger ones like World Bank and World Food Program are also very, very interested in this work. Just to give you a sense of the kind of things you can do once you have this model, the World Bank was very interested about what's going on in Somalia. That's one country where they don't have any data. They cannot even send people on the ground to collect more because it's too dangerous and they get kidnapped or killed. And so this is the map. We have images. We can fit them into the model. This is the map that we produce for them. We don't know how accurate it is because we don't have ground truth, but we're fairly confident that the predictions are reasonable because we've tried to see how well the model generalizes across countries. Now, I want to move on to the next topic, which is food security. That's, fighting hunger is basically the goal number 2 on that list of 17 Sustainable Development Goals. There is hundreds of millions of people around the world that don't have enough to eat every day. The situation is going to get worse as population grows. So here, a basic problem that we would like to answer is, given a field, how much food is that field producing, or how much food can that field produce? And as usual, in the developing parts of the world, we really don't have that kind of information. And so what we try to do is we try to build a similar system that takes as input cheap, passively collected, widely available data, images from satellites, and tries to predict using a similar architecture based on deep neural network plus a Gaussian process that is modeling spatiotemporal structure. We're trying to predict effectively how productive a field is going to be. And we can do it at the field level. The demo I'm showing here is actually done is aggregated at the county level. That's the Midwest in the United States. Every square corresponds to a county. And what the model is doing is it's predicting, as it gets new images from the satellites, it's predicting how, before the harvest, it's trying to predict how much soybean they're going to produce in that county for that particular year. And the surprising fact here is that if you look at historical performance of the model from, say, 2005 to now, this model does actually better than what USDA, the US Department of Agriculture, does. So USDA also cares a lot about this kind of forecasts. They do them every month. The way they do it is they go on the field, they collect data, they collect samples, they call up farmers. Historically, their predictions are slightly worse than what we can get using satellite images. The other nice advantage of satellite images is, of course, that our approach is much more scalable. So we've already applied it successfully in South America, and we're trying to extend it in Africa, where we're trying to handle small plots of maize in this case. So again, we show this kind of stuff to the World Bank. We submitted it to this World Bank Big Data Innovation Challenge that they held a couple of years ago. We were very happy to win the first prize at that competition. They were really, really excited about the potential of this work towards understanding food security challenges in Africa especially. And it's not just restricted to poverty and food security challenges. We've also applied this kind of idea to measuring infrastructure quality. That's another thing for which we know very little. Do people have access to electricity, roads, pipe water? We really don't know much. So we did this fairly large-scale study over 30 African countries. We had some ground truth data that you see on the left. Actually, the sampling is extremely sparse. That's not at scale. So if I were to show the dots at scale, you wouldn't see them. So we actually know very, very little about what's going on the ground, but we have some training data. We can fit one of these models based on the kind of ideas I talked about before, and then we can try to make predictions just using images. And again, the model is not perfect, but it's doing reasonably well. It's predicting reasonably well what's going on the ground from images. And now we can sort of use the model to fill in the gaps and figure out what's going on the ground and keep this information up to date. And we've applied this to many more problems, tracking population densities, counting tents in refugee camps to count population also there, identifying brick kilns, which are highly polluting in certain parts of the world, and also tracking and identifying crop diseases from space. Now, I'm not going to talk about these projects. Instead, I'll focus a little bit about what are the common challenges that we encounter when we think about these issues. One is that we often have very limited amount of labeled data. You need to do a survey on the ground. You cannot, it's not like something where you can just put them on Mechanical Turk, get more labels. Here you literally have a fixed number of labels, which is usually very small, and you have to build a model that predicts reasonably well just based on that. So we've done quite a bit of work in this space in my group, including using generative models to try to identify structure automatically, so like do representation and feature learning in an unsupervised way. We've also looked a lot into providing other kinds of supervision to these systems, including from constraints like physics or simulators. This is similar to what Jitendra mentioned before. So like if you know something about physics, then you have this kind of consistencies that your model needs to satisfy, and you can use this to provide supervision and get kind of good performances with much less training data. Again, I'm not going to talk about these works in detail. Instead, I'll focus on uncertainty quantification, which is critical if we want to use this kind of predictions to inform policy and decision-making in general. So the way we typically train a machine learning system is that we have a training data set, we have a set of examples, we have inputs, and the corresponding outputs. In this case, I have 4 data points, 3 are positive, and 1 is negative, the third one. We have a set of models. They are typically parameterized somehow by some weights. Each model will make a prediction at each data point, and predictions are often probabilistic. So the model will assign a probability that that data point belongs to the positive class versus or the negative one, I guess. There is a loss function that basically measures how good the predictions are. And intuitively, we would like the model to assign high probability to the positive examples and low probability to the negative ones. For example, this model parameterized by W1 is doing terribly because it's assigning high probability, 80%, to the only negative example and low probabilities to everything else. The way training works is that you search over the space of parameters to try to get better predictions. Maybe you move to, and you typically do it by doing some kind of say, gradient descent. Maybe you get a model that parameterized by W2, works a little bit better, and then maybe you find W3, which works reasonably well. It's assigning high probabilities to the positive examples and low probabilities to the negative ones. Now, the question is, how can we interpret these probabilities? We would like these probabilities to quantify how uncertain the model is about the prediction, how reliable the prediction is. Because, and that's really important if we want to use these predictions to inform decision making, right? We would really like to know if the model is confident in the predictions or not. How can we quantify this notion of this idea of reliably quantifying uncertainty? Well, the notion, the mathematical formulation of this idea is called calibration. The way to think about the problem is that we have a number of predictions made by our model over a bunch of inputs. What we can do is we can restrict ourselves to the points at which the model, let's say, predicted 60% probability. Then what we can do is we can check among those points where the model predicted 60%, how many of them are actually true. Right? In this case, 3 out of 5. So the empirical frequency here is 3 out of 5, which is 60%. And ideally, we would like these two numbers to match. We would like the predicted probability to match the empirical frequency when the model predicts that probability. That's a good property that we would like the model to have. It means that it's reliably quantifying uncertainty. Unfortunately, existing machine learning models are typically not calibrated. There are a number of papers, including fairly recently, showing that, for example, deep learning models are typically not calibrated, which means that you cannot trust the uncertainty estimates that are provided by deep learning models. So what we did with my postdoc and previously grad student Volodymyr is we looked into ways to improve the way machine learning algorithms quantify uncertainty. And in particular, we came up with a framework for taking any machine learning algorithm and make it uncertainty aware. So the idea is that we have a machine learning algorithm that will, in this case, we're thinking about the online learning setting. And this machine learning algorithm will produce probabilities, QT, which might not necessarily be calibrated. And so what we did is we came up with this idea, with this method that can basically take as input these probabilities and transform them into new probabilities PT, which have good properties, in the sense that they achieve the same loss as the original learner, they are guaranteed to be calibrated, and this works under very, very general assumptions, in the sense that you don't even need the data to be IID. It actually works essentially under the same assumptions under which online learning typically works, which is even against an adversary. Now, we've also extended this to regression problems, the kind of problems we are interested in when we try to predict, let's say, how rich or poor a certain location is. Again, here we would like the model not only to give us a number, but we would like to know how reliable that number is. And so one way to think about this is in terms of confidence intervals. So we would like the model to give us an interval and tell us, I think with 90% probability, the true outcome is in that interval. Unfortunately, again, existing models are typically not calibrated. So if you take, say, Bayesian neural networks and you look at the kind of intervals that these methods produce, they are not calibrated. This is a real-world example. It's showing how the 90% interval actually contains very few of the points. Most points are actually outside. They are red of this interval that is predicted by the model. So again, what we did in this recent ICML paper that was actually presented a couple of days ago is we provided a principled way to take uncalibrated, essentially uncertainty estimates from regression models and turn them into calibrated ones. And this is non-trivial because we need to stretch these confidence intervals in the right way such that it works on data points that the model hasn't seen before. But in practice, this works extremely well and helps on a range of problems where you want to use this kind of basically model-based reinforcement learning, where you want to use these kind of predictions to inform your decisions. Now, an additional challenge that we have to address is that we need to be able to compute these probabilities, and this typically involves some challenging probabilistic inference problems. The idea is that if you have a model with lots of random variables, such as a spatiotemporal one, where you're trying to predict multiple things at the same time. Computing probabilities, doing inference in these kind of models is expensive, and it typically involves the computation of some kind of high-dimensional integral corresponding to an expectation, effectively, where you have to consider all possible states of the world, and you have to marginalize over them. You have to assign a probability to each one of them, and you have to consider each one of them separately. The challenge is, of course, that the number of possible states of the world scales exponentially with the number of variables that you have, and this leads to basically intractability kind of results. So this is a widely studied problem, has been studied for a long time in a number of communities. Typically, it's addressed using either sampling methods like Markov chain Monte Carlo or variational approximations. These methods tend to work reasonably well, but they have a problem in the sense that you never really know how accurate the answers that you get really are. So in my group, we spent a lot of time thinking about a completely different paradigm, which is based on very different ideas. It's based on a combination of random projections and optimization. Again, I don't have time to go into the details and explain exactly how it works, but I want to give you the intuition for how the method approaches the problem. Let's say that you want to compute an integral, or you want to compute the area under the curve of that function that I'm showing on the left. This could be, let's say, a conditional probability, and you want to compute the marginal. So the way the algorithm works is that it first applies a random projection. This is constructed in a very special way by basically generating certain constraints with some very special properties. They need to implement a universal hash function. These random constraints will effectively sparsify the objective that you're trying to integrate. And then what we do is we use an optimization oracle to find the most likely state, to find the mode of that projected distribution. And we repeat this process a small number of times. And the surprising result is that if you do this a small number of times, you can provably show that you can estimate the original integral with very high accuracy, with very high probability. Now, the advantage here is that we can take advantage of decades of research and engineering into combinatorial optimization. And so by using existing solvers that were developed by the MaxSat community or constraint optimization community or operations research community, we can actually build an algorithm that works really well in practice because we can solve those optimization problems using these existing toolboxes. And we can get very strong guarantees because we know that if we can solve these optimization problems, which is generally hard, but in practice these solvers tend to work very well, then we can get a provably good estimate for the original integral. Now, ultimately, we want to use these predictions to help us make better decisions. This is itself a very interesting and leads to some very challenging computational problems. In my group, we've done work both on the methods development and on the applied side. In terms of method developments, one interesting thing you can do is you can use these kind of ideas to reduce inference to optimization to transform a stochastic optimization problem into a purely deterministic one. When you're dealing with a stochastic optimization problem, you're trying to make decisions that work well under uncertainty. Using that technique for dealing with the uncertainty, you can actually reduce a stochastic optimization problem to a purely deterministic one. And then you can, again, feed them into existing solvers. And in practice, this tends to work quite well. As an example of the applied work, we looked into helping farmers make better decisions. So we participated into a competition that was held at Informs, the main meeting from the operations research community, where basically the question is, what kind of seed varieties should you plant in order to maximize yield? And using the kind of models that we developed and this sort of optimization techniques, we were able to do quite well in that competition as well. Another area that I'm pretty excited about is the idea of using these predictions and these models to help us collect data in a more efficient way. The idea is that we typically do surveys by basically sampling at random, but if we have a sense of, we have some predictions and we have a sense of how uncertain they are, maybe what we can do is we can send the survey takers to the locations where the model is most uncertain. So these are some ideas that come from the optimal experimental design literature, the Bayesian optimization literature. There are some aspects that are different. For example, the fact that we are running multiple experiments in parallel, that we get the information back with delays. So we worked on developing the right theoretical frameworks to approach these problems. And we have some promising experiments in simulation, and we're hoping to actually try it out in the field. Our collaborators are very, very excited about using these kind of ideas to make their data collection process much more effective in practice, hopefully. For the final few minutes, what I want to do is I want to talk about human modeling. That's another key question that we need to address when we're trying to solve these kind of problems. The original motivation for me to think about this problem was a collaboration with economists at Cornell, University of Sydney, Kenya, and USDA. What they were trying to do is they were trying to build models to understand the migratory behaviors of certain tribes. These are migratory herders in Eastern Africa. And what they were trying to do is they were trying to build models to understand how they are affected by potential climate change, infrastructure changes, or policy changes like providing insurance policies. And they were interested in this kind of problem because these populations are extremely vulnerable to droughts and changes in the environmental conditions. Now, what got me interested in this problem is that they had collected a very unique data set. They had developed some custom GPS collars, and they were able, using these collars, they were able to track hundreds of different households for many years. And their question was to what extent they could predict their movements, their migrations, using environmental data like water availability, availability of pasture, and socioeconomic data like their age, education, things like that. So we've thought about this problem as an inverse reinforcement learning one. So we can think of them as being agents that are optimizing some reward function. As a result, they get a policy and some observed behaviors. The inverse reinforcement learning problem is the opposite one. We want to go from demonstrations, from trajectories, from GPS traces, and we want to infer a reward function that rationalizes, that can explain the observed behavior. The way inverse reinforcement learning algorithms typically work is that you start with a guess for the reward function, you run a planner, you compute an optimal policy with respect to that reward function, you get some behaviors, you compare them with that of the expert, with the demonstrations that you have in the data, and you try to update your reward to make your policy, to make your demonstrations more similar to the ones that you have in the data. So you can think of that step as being a gradient computation step, and that step on top as being actually taking a gradient step in that direction. Now, the challenge with this kind of approach is that it's very expensive because it requires solving planning, computing an optimal policy inside a learning loop. And so we looked into several ways to scale this up to the kind of problem sizes that we wanted to solve. One idea is that we can actually combine the planning process and the learning process into a single step. Basically, we take gradient steps on the reward before the planning is finished, while we still have sort of like incomplete information from the planner. This is similar to stochastic gradient descent. It's better to take many gradient steps, noisy gradient steps, that take one step based on a very accurate estimate of the gradient. This works very well in practice. It allows us to get up to 20 times speed-ups on the migratory problem, and that really allows us to scale it up to the kind of problem sizes we wanted to address. The other idea is that you can make additional assumptions. If you assume that you know the agents are optimizing policies in a particular class, parameterized somehow, then it's possible to use policy gradient methods directly. This avoids completely this double loop optimization. It's much more scalable. You can even apply it in model-free settings, and you can apply it to settings where computing an optimal policies is not feasible because maybe the state space is too large. The last challenge that we need to address is that we need to be able to compare the behavior of the expert with the data. This is typically done using features, which is fine in many situations, but if the state space is very high dimensional, maybe you want to work on raw pixels, this can be really challenging. And so what we did is we came up with this method based on adversarial training, where the idea is that we are going to train a separate classifier that will try to distinguish behaviors produced by our model from behaviors that are existing in the data. And in some sense, this is sort of like the main idea of deep learning. We're trying to automatically identify which features are useful and which ones are not by training some kind of flexible class of classifiers. And this works really well. We've applied it successfully to very high dimensional state spaces, including raw images. Here are some examples on the migratory herders problem on Ethiopia. This is anonymized for privacy, but sort of this is how we're trying to model the movements between camps, how they go to water points. This is also informed from satellites. We use satellites to figure out where green pastures are, and that's very helpful for improving the predictive accuracy of the model, which works really well. If you look at high-level statistics, it's capturing fairly well the structure in the data. So, yeah, this brings me to the final slide. I think I'm about out of time. So I hope I convinced you that AI can and should play a role in addressing these big societal problems of our times. These are hard problems, but it's really an exciting time to think about them because all these new technologies are really creating opportunities for coming up with unprecedented, completely new approaches to these problems. It's also interesting from a research perspective. This is uncovering interesting computational problems, and it's really opening up interesting opportunities for making deep contributions to the technical contributions to AI. I wanted to say that it's not anymore just an academic endeavor. We got so much interest from organizations, from small NGOs to large government organizations, that we couldn't keep up with it in an academic setting. So we started a company called Atlas AI to really scale this up and have as much impact as possible in the real world. This is the team. This is in the Palo Alto office. If you want to learn more, let me know if you want to work with us. And finally, of course, thanks to all the students and postdocs, without whom this would not have been possible, and all the various sponsors that funded all the research very generously. And I think that's it. Thank you very much. Thank you for staying until the very end, and thank you for the work.
Thank you, Stefano, for a very nice and inspiring talk. So I have actually a practical question. So for the satellite imagery work that you have done, I assume that when you use high-resolution imagery and also you want to provide predictions or detections for a large area, then you probably need to do like it seems like the computation time would be very high. So is that an issue, and how did you deal with it?
Yeah. So that's a great question. I mean, of course, there is a trade-off there in terms of like what kind of resolution of the images you want to use. In fact, some of the work we've been doing is based on multi-resolution kind of architectures, where we use both low-resolution images, which are updated very frequently, and high-resolution images, which might be updated very infrequently, maybe every few years. But it's relatively easy to kind of like combine, stacking together multiple kinds of inputs and use them all at the same time.
Thank you very much.
Thank you also for a very thought-provoking talk. I had a question about your general topic. Last year, we had Stuart's keynote on provably beneficial AI, and here we have your call for globally beneficial methods. To ensure scalability, what are your thoughts on general meta-reasoning methods to make sure that provably beneficial methods can scale and can achieve global scope?
Yeah, that's a great question. In fact, I'm also involved with the future of life and on that kind of research and trying to build provably beneficial methods. I think it's a very interesting and an important research question. I think this is sort of orthogonal. This is more thinking about, okay, with the technology that we have right now, what can we do to try to make a world a better place? I think the research that I'm doing for future of life is more it's more looking into the future and thinking about, okay, maybe 20 years from now or 50 years from now, how do we make sure that we have safe AIs and that we have the right frameworks and we have the right methods and the right algorithm to think about the problem in the right way. So for example, we've been looking at using SAT solvers and theorem proving ideas to get provable certificates that the models and the algorithms are doing the right things, these kind of questions, which I think are complementary.
Thank you.
Hi, over here. Hi, thank you for a very inspiring talk. I actually have a slightly different question, and that is work like this also has a political angle to it, even whether you like it or not. What advice do you have for the rest of us in terms of if we find ourselves caught in an application which has, which people may try and spin politically? How do we, what advice do you have?
Oh, that's a tough question. Yeah, right. I guess it really depends, and I don't know exactly what kind of applications you are involved with, but I think we are scientists fundamentally, and so I think it's different in the sense that we are just we publish everything. It's all open. All the stuff is open source. I think it might be I think the work should be should have as little as possible to do with politics, in the sense that everything that we write in the papers is hopefully objective and reproducible, and we're not trying to make any kind of statements about what governments should do or shouldn't do. Of course, there is a big push that they might want to push back, because the reason we have so little data, for example, in developing countries is because typically they have something to hide and they don't want you to know what's going on. But to the extent that we're doing science, we're just developing methods, I think maybe we can try to keep it as separate as possible.
Hi, nice talk. I'm curious about the interplay between these new forms of gathering data that we were never able to get before and decision making, like being able to actually solve problems that we weren't able to solve, and how those two might interplay in your opinion.
Yeah, that's a great question. I think a lot of the things I talked about and what we've been focusing on at the moment is mostly on the simpler part of the problem, which is let's use all these new data that are becoming available, whether it's satellites. We've also looked at social media data, cell phone, like CDR sort of like data that I haven't talked about in this talk, but there are a number of sort of like new data sources that are becoming available globally. They're passively collected, they're cheap to get, they clearly contain information about, say, the Sustainable Development Goals, and we finally have a way to actually make sense of them. Like, these are fairly unstructured, you're dealing with text, you're dealing with images, you're dealing with videos. Previously, a researcher had not access to a way to actually extract the significant bits from all these data streams. Now we finally can do it. And so we're literally just starting to scratch the surface, I think, in terms of like just building predictive models, which are already extremely useful. But then when we start thinking about, okay, how do we make better decisions, then I think it becomes harder, because you get also into causality kind of issues. Like, we're not able to say why this area is poorer or richer. Maybe we can say, okay, we can predict what it is, but then making causal statements is a lot harder. We're actually working a little bit on that with my colleagues in economics. They care, of course, a lot about these issues. And the way they see it is that with this kind of data, they can start to make also like kind of causal analysis, because now they hopefully know what's going on the ground, and they have very clever ways to think about randomization and be able to make this kind of like causal claims based on this new data.